So hello guys. So this is the continuation of the video that I uploaded before about plane trusses. So now we will go to 3.3, which is the member stiffness relations in the local coordinate system. So in the stiffness method of analysis, the joint displacement D of a structure due to an external load P are determined by using a system of simultaneous equations expressed in the form P is equal to SD, where S is called the structure stiffness matrix, and it will be shown subsequently that the stiffness matrix for the entire structure S is formed by assembling the stiffness matrix for individual member. So the stiffness matrix for a member expresses the force at the end of the member as a function of the displacement of those ends. So P, the external load P, is equal to the product of the structure stiffness matrix times the joint displacement. Okay. So for example here, this is the plane truss. Again, when we talk about the global, means the coordinate system of the whole structure, but when we talk about the local, considering point B and E, X is the reference of X is the diagonal one, and this is the Y. Again, if you consider the global, the whole structure, but for the global, it will be the whole structure. For the local, will be the individual member. So, for example, here, the Q1 is the local force. Okay? Q1 and Q4 are the local forces, or we can say the member end forces. And U1 and U4 are the member end displacement. The Q will cause U1 to displace, and Q2 the same, that causes U2 to have displacement. The same with Q3 and Q4. So considering each member forces and displacement in the local coordinate system, local means we are focusing on a specific member. Okay? So I will not discuss thoroughly about the derivation. So we will go to the derived one. Okay? So member end displacement and forces are numbered by beginning at the end of the member designated B, where the origin of the local coordinate system is located, with the translation and force in the x direction numbered first, followed by the translation and force in the y direction. The displacement and forces at the opposite end of the member designated E are then numbered in the same sequential order. So here, the end forces Q1 will be equal to K11U1 plus K12U2, 13U3, K14U4. What is K? K is the member stiffness and U is the end displacement. So by the definition of matrix multiplication, it will become Q is equal to KU. Okay? In which Q and U are the member force and member end displacement vector respectively in the local coordinate system, wherein K is called the member stiffness matrix in the local coordinate system. Small k means member stiffness in the local, and U is the end displacement in the local. The same is true with Q are the forces. So this is now, by substituting the foregoing values of the stiffness, we obtain the following stiffness for the members of plane trusses in the local coordinate system. So now, this is now the derived formula. K is equal to EA over L multiplied by 1, 0, negative 1, 0, so on and so forth. And this one, the value of K will be the member stiffness in the local coordinate system. So for example here, this is the truss. So the question is determine the local stiffness matrix for the members of the truss. Okay? This is very simple. So we want to determine the local stiffness for each member. So first we need to determine EA over L. So E is 29 KSI, meaning this is times 1,000 pounds per inch squared, then times 8 squared, 8 inches squared, then 216 inches. So it will be 1074.1 kips per inch. Or you can say also 1.074 times 10 to the 6 pounds per inch. Okay? This is the value of EA over L for member 1 and 2 because member 1 and 2 are the same. Okay? So now by applying the formula, the value of K is EA over L times 1, 0, negative 1, 0, 0, 0, 0, negative 1, 0, 1, 0, 0, 0, 0. So, this is the answer now. This is the answer for the local stiffness. Okay? For 3, 4, the same procedure, EA over L. Okay? Then, of course, for member 5 and 6, for 3 and 4, this is the answer, okay? For 5 and 6, of course, the length is not given. So, using Pythagorean, you can determine the value of length of the member 5 and the member 6. So, for member 5 and 6, this one, E is 29,000 KSI, A is 12 inch squared, L is 360 inch. So, applying that one, the local member stiffness K5 and K6 will have this one. Okay? EA over L multiplied by 1, 0, negative 1, 0, 0, 0, 0, negative 1, 0, 1, 0, and 0, 0, 0. Okay? So, let's have another example. If you do not have question, this is easy actually. So, let's go to 3.3. So, the displaced position of member 8 of the truss is given in figure 3.5b. Calculate the axial force in this member. Meaning, we want to determine the value of Q. Okay? Yeah, the value of Q for member 8. Okay? So here, given the truss, it's assumed that the displaced position is this one for member 8. Meaning, using 0.2 and 0.6, there is displacement for X and Y, which is 9 mm for the positive for the X direction and 12 mm for the Y direction. Again, we are in local coordinate system. That's why we have our own X and Y direction based on the orientation of the member. Diba? Supposedly, our X should be horizontal. If we are in the global, since we are in local, whatever the position of the member will be followed. So, these are given, this one and this one. Given to. So, at point 2, yeah. So, it goes down by 12 and it goes to the left by 9. And at point 6, it goes up by 16 and it goes up in Y direction by 12. Okay? So, this is later. So what we can do is, remember in the previous discussion, Q is equal to KU, right? Q is equal to KU, where Q is the member local force and K is the local stiffness and U is the displacement. Okay? So here, EA over L, 48,000 kilonewtons per meter. So you apply the formula which is EA over L multiplied by 1, 0, negative 1, 0, 0, 0, 0, negative 1, 0, 1, 0, 0, 0, 0. Okay? So now we have the value of K8. Okay? So now, let us look again for the member end displacement in the local coordinate system. Okay? here. Okay, with reference point 2, this part will be left part will be negative, down will be negative. Okay? Going in the upper position, positive, then higher, or I mean, yeah, higher in the direction of y will be positive. Therefore, here, you expect that the member end displacement will be negative 9, negative 12, positive 16, and positive 12. Okay? So here, we will form the matrix U. So negative 0.009. Okay? Meaning, this one. Okay? Because it goes in the left portion. Okay? So negative 0.009, because our unit is in meters, supposedly it should be in mm. Okay? If it is 9 mm, it will be 0.009 meters. So negative 0.009, negative 0.012, 0.012, and 0.016. Now, using the formula, Q is equal to KU. K is 48,000 multiplied by this matrix, multiplied by the end displacement Q. This will be the answer. Okay? This is negative, meaning you are in tension. Okay? So the member and forces, okay, are depicted on the brief diagram. Since the first Q1 is negative but Q3 is positive, the member H is subjected to tensile force. So the magnitude is 1088. This one. 1008 kilonewtons. It is tension. Why? See, this is negative, meaning the direction is going down. Then the other one is positive, going up. So what happened to the member? It experienced tension. That's why this is tension. Okay? So let's continue. So we have also the finite element formulation using virtual work. Sorry guys, we will just see the derivation, but we will not discuss on the formula. So we can go to coordinate transformation. Sorry. Finite element. We will just go to the important part. So from based on the derivation in the formula, we have now created a certain equation. So stress displacement relationship. Sigma is equal to E B times U. Okay? Where B is 1 over L negative 1010 and U is the member end displacement. So if you want to determine the stress sigma, you just multiply by the strain displacement matrix B times the member end displacement U times the modulus elasticity E. Okay? Then member stiffness matrix K. This is the one that we are saying. We already knew this one. So also the transpose of K, or the meaning they are symmetrical matrix. The transpose of K will be the same to value of K. Okay? So let's go to coordinate transformation. Meaning, we will transform the global to local coordinate system. So these are again the formula. Sorry guys, but I will proceed directly here. So recall that the stiffness matrix K is derived in the preceding section, relates member and force Q, and in displacement U described with the reference to the local XY coordinate system. So F are the global forces. So here what we can prove here, Q is the member the member forces in local, and F is the forces in global. Okay? Meaning you can calculate the value of Q if you already the value of F by multiplying F with the T, which is called the transformation matrix. And this is the formula. Okay? So the end forces is equal to transverse matrix times the global forces. Okay? We can also have another here. U, which is the end displacement, is equal to transpose matrix multiplied with the value of V, which is called the global displacement. Okay, global displacement. Then transformation from local to global. A while ago is transformation of, what is this one? Global to local coordinate system. So here you can determine the value of Q if you have the value of F. You can determine also the value of U if you have the value of B. Okay. Now transformation from local to global coordinate system. The value of the global forces is equal to the transpose of transformation matrix multiplied by the value of Q. So the transpose of the transformation matrix T times the value of Q. Okay? So let's have one example. So determine the transformation matrix for the member of the truss shown in figure 3.11. We want to determine the transpose matrix. Remember that the transformation matrix for member 1 can be obtained by using this one. So what is the transformation matrix? What is the formula for the transformation matrix? T. This one. The transformation matrix is cosine, sine, negative sine, cosine. Then just follow it. Okay? So let's apply to the previous problem. Cosine, sine, cosine 1, sine 0, cosine, sine, cosine, sine. This is for member 1. Okay? For member 1, yeah. The cosine is 1 and the sine is 0. Using the formula, if we are considering member 1, what is the coordinates of 2 and coordinates of 1? Coordinates 2 has a, point 2 has a coordinates of 6 and 0. So, 6 minus 0 divided by length, which is 6, is equal to 1. Then y2, both have 0, 0 coordinates. So, 0 minus 0 over length, which is 6, it will give you 0. So, apply the rule and this will give you. Member 2, the same. Just use the formula, member 4 and member 5. 6. It's easy, okay? So let's go to example 3.5. For the thrust shown, the end displacement of member 2, in the global coordinates, in the global, is 0.75, 0, 1.5, and -2. Now, calculate the end forces of this member in the global coordinate system. Okay? We want to determine the value of F. Okay? This is the unknown, the value of F. Having the global displacement at member 2 with this one. Okay? So, how to determine? We want to determine the end forces in global, meaning we want to determine F. Okay? And the formula for F will be T transpose times Q. T transpose times Q. So first, we determine the value of the transformation matrix at member 2. Then we will transpose it. Then we will multiply to the value of the end forces in the local coordinate system Q. So, this is later. So, EA over L. So, K is EA over L. This is 500. 1, 0, -1. Then, transformation matrix. Okay? Considering member 2, it will be, if we consider member 2, we need to know the coordinates of joint 3 and joint 1. At 3, it will be 9 and 12. Here is 0, 0. Okay? So, 4x will be 9 minus 0 divided by 15, the length, 0.6. Then the same with sine, 0.8. Now you have the transformation. Right? So again, we can determine the value of U by multiplying the transpose to the global and displacement U. So T2 times V2, you will have U2. Okay? So now, if we know already U2, we can now determine the value of Q using Q is equal to KU, where K is the one that we solved, this one, multiplied by U, which is this one. So now, the member of Q2 will be this one, 575, 0, -575, and 0. Okay? So this is in compression. So the member and forces is by calculating F is equal to TT, the transpose of the transformation matrix at member 2. So T transpose. Here, so what will be the transpose? This one will become here, 0.6, 0.8, 0, 0. Then this one will become -0.8, 0.6, 0, 0. This one will become 0, 0. 0.6 and 0.8, then 0, 0, -0.8, and 0.6. So F2 multiplied will become 345, 460, -45, and -460. Now, to show this one, okay, this one is the end displacement in the global, based on this given, 0.75 and 0, 1.5 and 2. Then in the local, the one that we calculated, local, 0.45, -0.6, -0.7, and 2.4. So this one. Okay. Then for the end, 575, compression, because this is positive, this is negative. Then for the global, in the global, 345, 460, negative 45, and negative 460. So, 345, 460, negative 345 because going to the left, then this is negative 460 going to the downward. Okay? So, next time I will continue on 3.6. So, for the time being, just watch the video and understand it. And if you have some questions or anything that concern about this topic, you can message me in Messenger. So thank you very much for listening.